This video is all about the equilibrium constant. It's a quantitative way to explore, describe, and model what's happening in a chemical system at equilibrium. Okay, so for a system at equilibrium, we can describe it with what's called the equilibrium constant, and that's what is shown here, K equilibrium, okay? So what it is it's more of an equation rather than expression actually, but it's an equation that describes the ratio of the products to reactants at a certain temperature, of course when a system is at equilibrium, okay? If the system is stressed or disrupted, the system will return to this ratio when it reestablishes equilibrium, unless that stress is a change in temperature. So one thing I'm trying to stress right off the top here is that the equilibrium constant KEQ is specific for a specific temperature, okay? It's specific for a temperature. The other really important thing probably to stress here, which I should additionally write, is this only applies when a system is at equilibrium. So it applies to a system at equilibrium. Okay, if it's not at equilibrium, then it won't necessarily follow this ratio as we predict. So we're looking at the ratio of concentration of products over concentration of reactants. So we can flesh that out in a little bit more detail here. Okay, so if we look in greater detail for a model system at equilibrium, so let's look at this sort of make-believe system at equilibrium here. So we would have reagent capital A, and then its stoichiometric coefficient would be little a, and so on. Reagent B, stoichiometric coefficient little b, and then product C, stoichiometric coefficient little c, product D, coefficient little d. So if we wanted to make the equilibrium expression for this, it would be the concentration of the products, C, and the product D, to the exponent of its stoichiometric coefficient from the balanced chemical equation little c, and the stoichiometric coefficient from the balanced chemical equation small lowercase d, divided by the concentration of the reagents, A to the A and B to the B. Okay, so this would all be numbers, of course, in the real scenario, but that's the model, and that's how you would come up with the equilibrium expression for any given reaction such as that. Okay, there are a few details and little caveats that we should mention here, which for one thing, this really only works if those are aqueous, okay, because we can't really take the concentration of things that are not aqueous, or if they're gases, we can also take the concentration of them. If they're a solid, we wouldn't include them in the expression. So let's say, for example, D turned out to be a solid. If D turned out to be a solid, then we would actually exclude it. We wouldn't put that term in there at all, because you can't take the concentration of a solid. It doesn't really make sense to do that. We don't describe solids in terms of concentration. We also don't describe pure liquids in terms of concentration. And if they're 100% pure liquid, then we also don't express it. So if it's a liquid, we don't include that either. So we don't include them. We don't include these pure solids and pure liquids. That would be one important thing to realize. We also don't, it comes up quite often, so I'll mention it. We also don't include like just regular pure water in there. Okay, you can't really take the concentration of water in water. That doesn't make sense. It makes your brain blow up. So we don't include that in the expression either. These are basically concentrations that we reserve for gases and aqueous things by and large. So a little bit more commentary about something we observed when we looked at Le Chatelier's principle is, again, if we look at an exemplar reaction like this one, just called the Haber process, producing ammonia. So see if you can pause the video and come up with what would the equilibrium expression be for this one. Okay, let's go through it. So you would have the product NH3 to the exponent 2, because it's got that coefficient 2 there. divided by the concentrations of the reactants. And you can put those in, of course, because they are gases, and gases, we can take the concentration of them. So it'd be nitrogen to the exponent 1, because basically there's a 1 out there, isn't there? And then hydrogen to the exponent 3. So this would be your equilibrium expression for this. I mentioned a couple things that are important off the hop, and one is that this is only changes with temperature. Okay, this only changes with temperature, and I'll kind of attempt to prove that to you or provide you some evidence for that. How do we know this only changes with temperature? Well, if you look at some of the other stresses we made with Le Chatelier's principle, one thing we did was we said you could change the concentration of one of these things. Okay, you could either, let's say for example, you could ramp up the amount of maybe I'll try and get a thick arrow there for this one. You could ramp up the amount of ammonia, NH3, and what we would observe then, okay, so imagine this went up, we would observe the equilibrium shift to the left according to Le Chatelier's principle to try and use up some of that additional NH3 that we added. And then, you know, consequently, we would see that go up, and we would see that go up, and we would see this one come down a little bit. So if you think about the math, if you kind of have your mathematical model mind on, the math would work out the same, and it would actually keep KEQ constant. Okay, so it would keep this constant, because the result of the NH3 increasing in the numerator would be that actually the values in the denominator increase in a corresponding manner, and it keeps the math consistent. Okay, if we changed, and I'll use green for this one, if we changed the pressure, which presumably we would have to do with a change in volume. Well, you might remember that concentration is basically moles over volume, okay? So that's a really important thing to realize. If we are changing volume then, watch this. Let's say we increase the volume, okay? So let's say we're going to go ahead and say, yeah, let's increase the volume. That's going to result in a decrease in pressure, but mainly I want to focus on the volume factor because I'm going to try and correlate it to concentration. So if we increase the volume, okay, what happens to concentration? Well, we know if we increase the denominator, a concentration is going to fall, right? Okay, so what would be happening is we would be decreasing the concentration of all of them in a way, right? And so since concentration is the key thing that's in the equation, all of the concentrations would decrease by a combined effect, which would still keep the K equilibrium constant. Okay, so because they're decreasing and because we consider their stoichiometry, the math would continue to work out to keep K equilibrium constant in the blue situation and the green situation. Where things would be entirely different is if we changed temperature. So let's say, for example, for the temperature factor, we said, yeah, let's increase temperature. Okay, so if we increase temperature, it's like increasing the energy. Now the whole thing is going to shift to the left, right? Because it's going to try and use some of that heat we added. It's going to try and use up some of that thermal energy. And literally all that's going to do is drop down the concentration of the product and increase the concentration of the reactants, which would change K equilibrium entirely. There's no mechanism there. There's no built-in structure to keep K equilibrium constant in that scenario. So what we would see is that a temperature changes or results in a new equilibrium constant. All right, so let's take a look at a proper system with amounts detailed and everything else. So let's say we have 0.60 moles of SO3, 0.020 moles of SO2, and they're present in a 2-liter flask at equilibrium. Of course, we're going to assume all those things are proper to establish the equilibrium, like the flask is closed, nothing can enter or exit, no matter that is. And then what we're being asked to do is calculate the equilibrium concentration of O2 if we know the equilibrium constant is equal to 789 for this system, and then here is the balanced chemical equation for that system, okay? So I think we should begin by writing the equilibrium expression for this. We know it is going to be concentration of the product, SO3, to its exponent, stoichiometric coefficient from the balanced chemical equation. Then the divided by the concentration of the reactants to their coefficients, SO2 to the 2 and O2 to the 1. Okay, now in this case we have real numbers, so we can fill them in. What is the concentration then of SO3? Well, the SO3 concentration is going to be equal to the number of moles of SO3, 0.60 moles, divided by the total volume that it's in, which it's in a 2-liter flask. Okay, you don't have to divide up that volume or anything among them. Remember that the gas particles are free, and if you were to pump them into a 2-liter vessel, they're going to occupy, to some extent, the entirety of that. I guess I shouldn't say to some extent. They're going to occupy the entirety of that vessel in a fairly evenly distributed manner. Okay, so there's your concentration of SO3. If you pump that into your calculator, or really it's just dividing by 2, so it's easy enough. It's 0.30, 2 sig figs, by the way, and that's moles per liter, so capital M. You can do the same with the SO2. Okay, with the SO2, you're going to see that as detailed here. It's 0.02 moles over 2 liters, so that's going to give you a concentration of 0.01 mole per liter. Okay, then we're going to put that in. We know that K equilibrium is 798, so we can sub these values in. 0.30, remember it's to the exponent 2, divided by 0.010 to the exponent 2, times whatever the concentration of O2 is, and then we can just rearrange that equation and solve for the concentration of O2. And so if you do that, you're going to multiply by this and divide by that and get to hopefully you can figure out the algebra on it. But the O2 concentration is going to be 1.1 moles per liter. Okay. Now remember that K equilibrium does stay constant here. There's no reason for it to change unless we change temperature. All right, so have a look at this one. It's my favorite equilibrium again, the Haber process. So we can see here that this is an exothermic process, right, in the forward direction. And we can see at 25 degrees Celsius, this is a bit arbitrary. I don't know this for a fact, but we're going to say the equilibrium constant is equal to 100. So the question is, what would happen to the value of the equilibrium constant if the temperature were 0 degrees Celsius? So we should be able to predict this. Well, we would be saying, essentially, if we're making it colder, right, we are kind of drawing down that energy, right? We are removing energy from the system in a way, and so we would expect that system to shift to the right, okay? So we can write this out. So we are removing energy, okay? We're removing energy. It would shift to the right. So what happens, and this isn't really even what the question is asking, I just want to make it clear for you. So it would shift to the right. What does that mean for the equilibrium constant? Hopefully you realize that means that we'd be increasing the numerator in the equilibrium constant, and so the K equilibrium would increase, okay, as a result. If you're not sure about that, remember that this value is ultimately going to increase and these values are ultimately going to decrease. Okay, so you're increasing numerator, you're decreasing denominator. Both of those factors result in a larger number, so your K equilibrium would increase. In green here, let's talk about this one. What would happen if we injected nitrogen gas into the system? Well, this is like according to Le Chatelier's principle, this is like increasing the concentration of nitrogen. So it would shift away from that added amount. It would shift to the right. Okay, so we can say that. Equilibrium would shift to the right. Shifts right. What would happen to the equilibrium constant, though? Remember, the equilibrium constant would not change. Would not change. And if you're looking for the rationale for that, remember that although we increased N2, then what would happen correspondingly is we would see a decrease in hydrogen gas because some of that hydrogen gas is being used to react away the N2, and we would see an increase in ammonia, in NH3. And so those offsetting changes, that would be the knock-on effect according to Le Chatelier's principle, would help keep K equilibrium at a constant value for all changes other than if we changed temperature. It is often helpful to sketch out the little plots of how this might look, concentration versus time here as well. Okay, so in this one, if we had NH3, maybe I made it too small. Let's see. We had our N and our H2. For this one, we inject in nitrogen. So we're injecting that in. What's going to happen? Some of it's going to get used, and it's going to establish a new position. Hydrogen is going to go down, and nitrogen is going to go up. Okay, so it would be something like that. For the blue one here, really, if we change temperature, all we would see, this is going to get a little bit condensed, but I think it'll work. All we would see is instead of any initial change, they would all just start to change at the moment of temperature changing. So we would see this one go up, and we would see these ones go down, right? And then a new equilibrium would be established there. Okay, finally, just make sure you can interpret what the equilibrium constant actually means. So if you're just presented that value as a number, so let's say you hear, okay, for a certain process, the equilibrium constant is equal to 80, okay? That's a lot greater than 1, and we would say this is a very large equilibrium constant, which means that the products are favored. Remember, this means that the numerator is much larger than the denominator if it's well over 1. And so products are favored, or we'd say the equilibrium lies to the right, meaning the reaction basically goes to completion or more or less to completion. Whereas on the flip side of that, if you find out that the K equilibrium is very small, maybe it's like, something much less than 1, well, this is telling you that there's much more denominator than there is numerator. In other words, the reactants are much more significant than the products, or the reactants are favored, and this equilibrium lies to the left. In other words, it hardly proceeds. And so the gold standard is to look at how K equilibrium, look at how the equilibrium constant, the equilibrium expression compares to 1. If it's well over 1, mostly products. And if it's well under 1, it's mostly reactants. Okay, I hope you found this helpful in understanding the equilibrium constant.